You are probably acquainted with the graph of sine x, the value of which oscillates between +1 and -1 as we move to the right. We can always calculate the derivatives of this function, but let's see what the derivative of the function implies from a somewhat different perspective. The derivative of a function at a point is the slope of the tangent line at that point. At the origin, the angle that the tangent line makes with the x-axis is 45 degrees. The slope of the tangent line is related to this angle and is equal to tan 45, that is 1. Though the angle itself is not a direct measure of the slope, it gives us an idea of how the slope of the tangent line changes as we move to the right. As we move along the x-axis, the slope decreases and becomes 0 at the maximum point. If we continue further, it becomes more and more negative. Then it becomes less and less negative and is equal to 0 at the minimum point. Now the slope starts to increase and reaches the value that it had in the beginning. Now the tangent line is at the same state as it was in the beginning. So the slope seems to have a periodic characteristic, that is, the line repeats its state of inclination after a certain interval. Let's keep an eye on exactly how the value of the slope of the tangent changes as we move to the right. At the origin, the value of the slope is maximum, being equal to 1. For the sake of convenience, let's replace sine x with y and the slope with dy by dx. We will follow the path that is being traced by this point, the height of which is the value of the slope of the function. At first, the slope decreases and becomes 0 at the maximum point. Then it becomes more and more negative and is equal to -1 at this point. Then it becomes less and less negative and is equal to 0 at the minimum point. After that, it reaches the value 1. The inclination of the line at this point is the same as it was at the origin, and the height of the point is the same as it was in the beginning, implying that the new function has the same period as that of the original function. Both functions have the same period. They repeat their patterns after an interval of 2π. Observe how the value of the slope oscillates between +1 and -1. Also observe the points where the inclinations of the tangent lines are the same. The values of the slopes of the tangent lines correspond to these 3 points that are at the same height from the x-axis. The graph of the new function is the well-known graph of cos x. This new function is called the derivative because it's derived from the old function. Visually, both functions appear to be very similar to each other. So let's compare the two functions and analyze the difference between them. The nearest neighboring peaks of the two functions are at a distance of π/2, or simply 1.57. So if we move the new function to the right by an amount of π/2, it will superimpose on the original function. So you can say that the derived function is the same as the original function, but shifted to the left by an amount of π/2. Since both functions are periodic in nature, they can be superimposed in infinitely many ways. Now we intuitively understand the difference between the derived and the original functions. Let's try to find out a mathematical expression relating the two functions, because it's good practice to be able to translate an intuitive visual idea into precise mathematics. Now the derivative of the function is the function itself, but shifted to the left by an amount of π/2. Observe what happens when the input value of the sine function changes. An addition in the input value corresponds to a horizontal shift to the left, and a decrease in the input value corresponds to a horizontal shift to the right. So an increment in the input value by an amount of π/2 corresponds to a horizontal shift to the left by the same amount. This is the first derived function, or more specifically, the first derivative of sine x. Since the derived function repeats its pattern after an interval of 2π, we get the same function as we shift the graph horizontally by the same amount. Decreasing the input value by an amount of 2π shifts the graph to the right, leaving it unchanged. Now let's analyze further functions that can be derived from this new function, which itself is derived from the original function. Now the derivative of this derived function is the function itself, but shifted to the left by an amount of pi by 2. This is the second derivative of the original function. Again, the derivative of this newly derived function is the function itself, but shifted to the left by an amount of pi by 2. So the first derivative of sine x corresponds to shifting the graph to the left by an amount of pi by 2. The second derivative corresponds to shifting the original graph to the left by 2 times pi by 2. The third derivative corresponds to shifting the original graph to the left by 3 times pi by 2, and so on. So the nth derivative of sine x corresponds to shifting the original graph to the left by an amount of n times pi by 2. This is the generalized mathematical expression we have been looking for. This term here corresponds to a horizontal shift. You can think of taking a derivative of sine x as an operation that brings about a horizontal shift of the graph to the left by an amount of pi by 2. So doing this operation n times corresponds to shifting the original graph to the left by n pi by 2.